Right triangles are the doorway into trigonometry because they give shape to the ratios we use again and again. The opening slide already sets the tone. This is not just about formulas, it is about understanding how a triangle's angle controls the relationship between its sides. Once that connection is clear, the whole chapter starts feeling much more logical. In CAT style questions, this is the kind of topic where visual understanding saves time later. A right triangle is the cleanest place to study trigonometry because every angle and side has a fixed role. The angle acts like the input, the trig ratio is the rule, and the missing side becomes the output. That is the real flow behind the topic. When the slide says angles dictate proportions and sizes change while ratios stay stable, that is the core idea to remember. The geometry may stretch, but the ratio logic remains intact. The deeper reason trigonometry works so well is that it combines two powerful ideas: the Pythagorean relationship and similarity. Pythagoras locks the three sides together, while similarity guarantees that ratios stay the same across different sizes. So, trigonometry is not random memorization, it is a system built on consistent geometry. The final conclusion on the slide is excellent. Angle decides the ratio, and size only scales the length. That distinction is what makes the topic elegant. SOH, CAH, and TOA are the three building blocks that every student should know instantly. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. The important thing is not just remembering the words, but understanding what they mean on a triangle. The hypotenuse is always the longest side, and sine can never exceed 1 because it is a ratio to the largest side. That small insight often helps in checking whether an answer is reasonable. This challenge problem is a classic line of sight question. A tower of height 50 square root of 3 meters and a ground distance of 50 meters form a right triangle with the elevation angle given as 60 degrees. The task is to find the line of sight distance, which is simply the hypotenuse. These are standard exam questions because they test whether you can identify perpendicular, adjacent, and hypotenuse correctly before applying the ratio. The setup itself is the main test here. The standard solution does the job in a straightforward way. First, identify the adjacent side and the target hypotenuse. Then, apply the cosine formula and finally solve for the unknown length. That gives the answer cleanly, 100. This method is reliable, and reliability matters, but the slide also reminds you that it can cost valuable time. In a timed exam, a correct method is good, but a quicker pattern-based method is better. The topper's approach shows why standard triangles matter so much. A 30-60-90 triangle has a fixed side ratio of 1 to square root of 3 to 2, which means you do not need to compute everything from scratch. If the adjacent side is 50, the hypotenuse is immediately 100. That is the power of memorizing standard ratios. They turn a full calculation into a one-line answer. This is exactly the kind of shortcut that makes a huge difference in competitive exams. Elevation and depression angles are equal, and that is one of the most important conceptual facts in trigonometry. The correct approach is always to sketch the horizontal line of sight first, because that makes the geometry visually clear. The trap is to measure the depression angle from the vertical axis, which is wrong. That mistake is easy to make under pressure, so the slide's warning is worth taking seriously. If you draw the horizontal first, you avoid most confusion immediately. The speed hack here is to stop doing unnecessary inverse trig calculations when standard triangles already give the answer. The 45-45-90 triangle gives the ratio 1 to 1 to square root of 2, and the 30-60-90 triangle gives 1 to square root of 3 to 2. These two patterns cover a large number of exam questions. The broader takeaway is simple. Visualizing the standard ratio is faster than calculating from scratch every single time. That mental picture is a real scoring advantage. The identity sine squared of theta plus cosine squared of theta equals 1 is one of the foundational formulas in trigonometry. It comes from the Pythagorean structure of the right triangle itself, so it is not a separate trick but a direct consequence of the geometry. Sine squared and cosine squared together complete the unit relationship. This is the kind of identity that later becomes very useful in algebraic simplification and advanced problem solving. A strong understanding of this one formula pays off repeatedly. This cheat sheet ties everything together beautifully. The core formula set is SOHCAHTOA. The key rule is a squared plus b squared equals c squared. And the standard triangle shortcut is the 1 colon square root of 3 colon 2 pattern. The observation about elevation matching depression is another key exam point. And the final line says the real lesson clearly. Master the ratios and the CAT exam becomes much easier to control. That is the right mindset to end on, because trigonometry rewards recognition, not panic. Trigonometric functions are not just formulas to memorize. They are a way to describe motion, rotation, and periodic behavior. The visual of the circle and the angle already hints at the deeper idea. Every angle corresponds to a position on a circle, and that position creates predictable patterns. If you approach this topic through visualization rather than memorization, it becomes far more intuitive and much faster in exams. The entire structure of trigonometry rests on a simple flow. Angle leads to a point on the unit circle, and that point gives you trigonometric ratios. Once that mapping is clear, even complicated wave patterns become predictable. The key exam insight here is powerful. Connect every formula back to geometry. If you can picture the circle, you rarely need to rely on blind recall. There are three pillars holding this chapter together: radians, the unit circle, and periodicity. Radians link arc length directly to angle. The unit circle extends trigonometry beyond basic triangles, and periodicity explains why these functions repeat in cycles. The most important takeaway is that 360 degrees equals 2 pi radians, and that conversion is something you should be completely comfortable with. It shows up repeatedly in questions. The identity sine squared theta plus cosine squared theta equals 1 is the backbone of trigonometry. It comes straight from the Pythagorean theorem when applied to the unit circle. Sine represents the vertical coordinate, cosine the horizontal coordinate, and together they always satisfy this relationship. Many advanced identities and simplifications are built on this single idea, so treating it as a core principle rather than a formula is the right approach. This problem introduces a sine-based motion model, a wave describing the vertical displacement of an ocean buoy. The amplitude is 2 and the angular frequency is pi over 3. The goal is to find when the wave reaches its maximum height for the first time. The structure of the equation already tells you everything. This is not just algebra. It is a time-based periodic motion problem. Recognizing that shifts your approach immediately. The standard solution follows a direct path. Identify that maximum height equals amplitude, set the sine expression equal to 1, and solve for time. This leads to a clean answer of 1.5 seconds. The steps are systematic and reliable, especially if you are comfortable with unit circle values. But as the slide suggests, this approach takes time and can slow you down under pressure. A faster approach comes from visualizing the sine wave. The sine function reaches its first peak at 1/4 of its period. So instead of solving equations, you compute the period and directly take a quarter of it. Here, the period is 6 seconds, so the peak occurs at 1.5 seconds. This method bypasses calculation almost entirely. The moment you think in terms of wave behavior instead of equations, the solution becomes immediate. Quadrants control the sign of trigonometric functions, and that is where many mistakes happen. Cosine is even, meaning it absorbs negative signs, while sine and tangent follow quadrant-specific behavior. The ASTC rule, all, sine, tangent, cosine, helps you remember which function is positive in each quadrant. Another useful habit is mapping angles to quadrant 1 using reference angles, which simplifies evaluation significantly. This shortcut question highlights how powerful reference angles can be. Instead of constructing the entire unit circle, you identify that 5 pi over 6 lies in quadrant 2 and has a reference angle of pi over 6. Since sine is positive in quadrant 2, the answer becomes simply 1/2. This is much faster than deriving everything from scratch. The key idea is to memorize quadrant 1 values and use symmetry to get the rest. The general sine function, y equals a sine of b times x minus c plus d, explains how waves transform. A controls amplitude, b changes the period, c shifts the graph horizontally, and d moves it vertically. This formula is essential for understanding graphs and interpreting real-world signals. Once you see how each parameter affects the curve, even complex wave questions become manageable. The final slide brings everything together. The core identity, the tangent relationship, and the period formula form the backbone of problem solving. The table of standard angles is helpful, but the final message is even more important. Do not memorize blindly. Visualize the unit circle and derive results when needed. That mindset reduces errors and improves speed at the same time.